Once upon a time, there was a king. He had a mathematician in his court. This clever mathematician invented the game of chess and presented it to the king. The king was delighted and asked the mathematician to name a reward, any reward. Nothing was too big. The mathematician looked at the chessboard consisting of 64 squares and asked for some rice. The king looked perplexed. Rice? What kind of gift is that? The mathematician then added that the rice needed to be given to him according as this condition. 1 grain of rice in the first square, 2 grains of rice in the second square, 4 grains in the third square, 8 in the fourth, and so on until the last square. The king was a bit offended at the simple request, but he told the mathematician, "If this is your wish, I will grant that." Will the king be able to grant this request? Welcome to another episode of the Maths Factor, where we're going to explore the intricacies of algebra. This is no textbook journey. We'll tell you stories, riddles, and real-life problems to bring this subject to life. Keep watching to see algebra like never before. Back to our king and his mathematician. He starts doling out the rice according to his condition. And so, on the first day, the mathematician got 1 grain. He got 2 in the second, 4 in the third. And the king looked amused at the stupidity of the seemingly brilliant mathematician. If we progress along the same lines, on the 6th day, the mathematician will get 32 grains of rice. On the 8th day, he will get 128 grains. And on the 16th day, he will get 32,768 grains, which is about 1 kg of rice. But soon the numbers started increasing, and the king started getting restless. Soon the king realized that he would need to resign on his promise. He just would not have enough rice to complete his gift. Now, if he had some understanding of algebra, he clearly would not have been in the situation he was in. Let's see what he should have been able to work out. The first square is 1, the second 2, the third 2 into 2, which is 4, the fourth square 2 into 2 into 2, or 2 cube, or 8. So the number of grains in the 64th square is 2 to the power of 63, which is, wow, that's really large, isn't it? Well, the story is a sad ending. Not only was the king unable to keep his promise, he was so annoyed with our mathematician that he had him beheaded. Much like the king, most of us don't get the point of algebra, do we? It's something we plow through in school and discard at the first point that we can. But we could shift perspective and look at algebra as a mystery, as a search for the unknown x. Let's put this in a more real context. Here is Tanay carrying a bunch of balloons. He accidentally lets go of 3 and is left with 5 balloons. So how many balloons did Tanay have to start off with? Let's call that number the mysterious x. We know that when 3 balloons were taken away, we are left with 5 balloons. Now, if we work the equation out, we get x is equal to 5 plus 3, which is equal to 8. So we know that Tanay has 8 balloons. Besides helping Tanay figure out how many balloons he has, algebra powers much of our lives, starting from working out quantities in the kitchen to converting measurements from one system to another. Many fundamental principles in physics can only be understood using the tools in algebra. Modern algebra is applied in and propels almost every branch of mathematics. It is to mathematics what mathematics is to science. Now, a lot of algebra originated from the Middle East, from Persia to be precise. And one mathematician is central to this story. His name is Muhammad ibn Musa al-Khwarizmi. He was born in 780 AD in Khwarizm, a small town in present-day Uzbekistan. He and his family then moved to Baghdad. At that time, Baghdad was under the patronage of the Abbasid Caliphs. The Caliphs for 3 generations had put together a magnificent scientific academy called the House of Wisdom at Baghdad. Much learning from all over the world was centered here through this time. Al-Khwarizmi flourished in this atmosphere. He was a scholar at the House of Wisdom and was later appointed the Caliph's librarian. He wrote a famous book called Hisab al-Jabr wal-Muqabla in 825 AD. The word algebra comes from al-Jabr. Now, Khwarizmi's books came to form the foundation of algebra and actually established it as a separate discipline. In fact, they constituted university textbooks till the 16th century. Since the books were not footnoted, it is tough to trace the sources of his information, though he was clearly influenced by both Indian and Greek thought. Now, the title of his book teaches us algebra right away. Let's look at that a little more closely. Al-Khwarizmi's book was called Hisab al-Jabr wal-Muqabla. In Arabic, Jabr is an algebraic operation of restoration, which is the act of subtracting terms on either side of the equation. Take the equation x minus 2 is equal to 12. Now, we take the 2 from the left-hand side and restore it to the right-hand side by making x is equal to 12 plus 2 is equal to 14. The other word in the title, Muqabla, means balancing and is the act of cancelling like the terms on opposite sides of the equation. Let's take this one. X plus y is equal to y plus 7. Now we get x is equal to 7 by cancelling or balancing the 2 sides of the equation. Eventually, the Muqabla was left behind, and this type of math came to be known as algebra in many languages. In fact, the entire title has been translated to mean the Book of Restoration and Balancing. On our journey through algebra, we were exploring Al-Khwarizmi's famous book that translates to the Book of Restoration and Balancing. Now, the very same idea of restoration and cancelling comes up in Lewis Carroll's classic Alice in Wonderland. And this is not as curious as it first appears, since Lewis Carroll, who was in reality Charles Dodgson, was actually a mathematician at Christ Church College, Oxford. Let's enter Wonderland and see what actually happens to Alice. And more importantly, what that had to do with mathematics. Alice plunges down a rabbit hole, and this kickstarts her adventure. She meets an advice-giving caterpillar who is beside a large mushroom and is smoking a long hookah. At this point of the story, Alice has already experimented with proportionality and has eaten a cake that made her grow bigger and has drunk the liquid that made her grow smaller. The caterpillar then gives her some additional information. One side will make you grow taller, the other side will make you grow shorter. One side of what? The other side of what? Thought Alice to herself. Of the mushroom, said the caterpillar, just as if she had asked it aloud. And in another moment, it was out of sight. Alice, clearly a risk-taking young woman, samples the mushroom. However, when she eats from one side, she discovers that growing taller translates to a neck being stretched. and growing shorter translates to a torso shrink. She concludes that in order to regain her proper size and proportions, she must ensure that she eats exactly the right balance of each side of the mushroom. So what does the sequence, psychedelic as it seems, have to do with algebra? Now, if we go back to our discussion of the title of Al-Khwarizmi's book, it translates to restoration and reduction. Carol experiments with Alice's reduction, which is reducing her size to get her through the door, and restoration as she seeks to find something to restore her to her original size. Now, many mathematicians believe that Carol's writing was an exploration of new modern mathematics that were emerging in the mid-19th century. Now, enough of Alice and her absurd adventures. Let's head back to the evolution of algebra in the Middle East. One of the areas where algebra came in very useful was Islamic inheritance law. Let's try and see why. Consider this problem. Here is a man who had 2 sons and 2 daughters. Then he dies and leaves all his money to his 2 sons and 2 daughters. His wife is already dead. The rule of the law is that each son gets twice as much as the daughter, but the sons have to get the same amount as each other. Now, if he has 24,000 gold coins, how much will each of them get? Now, let's use algebra to try and solve the problem. If each daughter inherits X coins, then each son inherits 2X. With 2 sons and 2 daughters, our equation will read 2x plus 2x plus x is equal to 24,000. 6x is equal to 24,000 implies that x is equal to 4,000, which means that each daughter gets 4,000 and each son 8,000. A bit gender biased, but it does show us how useful algebra can be. We have traveled to the Middle East to see the contributions of Al-Khwarizmi. Now let's travel back in time to India in the 7th century to explore the mathematics of Brahma Gupta, an Indian scholar. He was from the state of Rajasthan of northwest India. Since he is from Bhilamala, he is often referred to as Bhilamalacharya. Now, Brahma Gupta wrote many important works focusing on mathematics and astronomy. In fact, he became the head of the astronomical observatory at Ujjain in central India. Brahma Gupta introduced extremely influential concepts to basic mathematics, including the use of zero in mathematical calculations and the use of mathematics in describing and predicting astronomical events. Much of what he worked on was not even thought about in the West until 1,000 years later. Much of his work was composed in elliptic verse. He once said, "As the sun eclipses the stars by his brilliance, so the man of knowledge will eclipse the fame of others in assemblies of people if he proposes algebraic problems, and still more if he solves them." A lot of this knowledge traveled from India to Arabia and influenced the thinking of scholars like Al-Khwarizmi. On our journey through algebra, we've explored the work of Brahma Gupta and Al-Khwarizmi. We next move to look at Diophantus, a famous mathematician from the 3rd century. Now we know pretty little about Diophantus' life, except his age, which is couched in the form of a riddle. Sounds intriguing? Let's check out the riddle. Quite the riddle. Let's take it a line at a time and try and decipher this. To do that, let's presume Diophantus' age is X. Now, God gave him his boyhood 1/6 of his life, means that his youth lasted 1/6 of his life. 1/12 more his youth while whiskers grew rife, means he grew a beard after 1/12 more. And then yet 1/7 ere marriage began, tells us that after 1/7 more of his life he married. In 5 years there came a bouncing new sun, which is quite clear in itself. Alas, the dear child of master and sage, after attaining half the measure of his father's life, chill fate took him. Sorrowfully tells us that the son lived only half as long as his father. After consoling his faith by the signs of numbers for 4 years, he ended his life. And we realize that Diophantus died 4 years after his son. Now we can use this information to craft this equation. And if we keep simplifying this like this, we reach the conclusion that Diophantus lived to the age of 84, while his son only lived to be 42. Now let's move to an area of algebra that sounds complex but is beautifully simple. Quadratic equations. A quadratic equation is a very simple one where we have a square of the unknown, which means we are working with an x square, not just an x. The Latin word quadratus means square. So a general quadratic equation is ax squared plus bx plus c is equal to 0, where a is not equal to 0. Now the solution with this is pretty complicated. This is the answer. Let's take a simple example and try and work out a more comprehensible way of looking at it. Take the equation x squared plus 6x is equal to 27. Let's try and solve it. If x is equal to 1, then 1 plus 6 is not equal to 27. So 1 is not the solution. If x is 2, then 4 plus 12, which is not equal to 27. So 2 is not the solution. We could keep going like this, but let's look at it differently. Think of the first term as the area of a square with side x. Now, the 6x is the area of a rectangle with the sides of 6 and x. Or we can split it up into two rectangles where one side is x and the other side is 3. Now if we attach the rectangles onto the square, we'll produce an area which is equivalent to x squared plus 6x. Now according to our opening equation, this is equal to 27. Quite right, 27. Now look at the missing corner. Aren't you itching to fill it with another square? Go ahead and do that. This square has a side of 3, and so our square has an area of 9. We need to add this to both sides. Now the right hand side is a square with the side measuring x plus 3. So we can write the equation as x plus 3 whole square is equal to 27 plus 9, which is equal to 36. Now the whole complexity of the quadratic has been ironed out, hasn't it? Now very simply, x plus 3 is equal to 6, which means x is equal to 3. This solution was actually suggested by Al-Khwarizmi, and what completes its elegance is that it can be used as a solution for any quadratic equation. I need to add in just one point that Al-Khwarizmi missed. When we look at the square root of 36, both plus 6 and minus 6 are possibilities. During Al-Khwarizmi's time, knowledge of negative numbers was not so prevalent. So, the other solution to a problem is x plus 3 is equal to minus 6, so x is equal to minus 9. And that ties in beautifully with the starting formula and explains why there is a plus and minus option before the square root. Now what happens when the equations get higher? Say a cubic equation. It's of the form ax cubed plus bx squared plus cx plus d is equal to 0, where a is not equal to 0. Now let's look at a concrete example. 2x cubed plus 3x squared plus x plus 1 is equal to 0. How can we solve this? If x is 1, then 2 plus 3 plus 1 is not equal to 0. So 1 is not the solution. If x is 2, then 16 plus 12 plus 2 plus 1, which is not equal to 0. So 2 is not the solution. In Europe at this time, mathematical contests in public forums was common. mathematicians tried to solve equations such as these, and the winner earned valuable money for these. Let's explore one such contest in the Republic of Venice during the 16th century between Niccolò Fontana, Tartaglia and Antonio Maria Fiore. Fiore had learned one way of solving cubic equations from his teacher. Curiously enough, a few days before the contest, Tartaglia managed to find the general method of solving another kind of cubic. At the contest, the problems Tartaglia posed were all of the second type, and so he emerged the winner. Later, however, both methods were published together in a book called Ars Magna by Girolamo Cardano, another famous mathematician. Let's fast forward another 13 years. Cardano had a student called Lodovico Ferrari. Ferrari managed to solve the quartic, which are equations where x goes up to the power of. Then, in a repeat of history, Ferrari challenged Tartaglia to another public contest. Tartaglia was extremely reluctant to dispute with Ferrari, still a relatively unknown mathematician, but finally agreed. On 10th August 1548, the contest finally took place. By the end of the first day, it was clear that things were not going Tartaglia's way. Ferrari clearly understood the cubic and quartic equations more thoroughly and won the contest. After all this, the solution to cubic equations is usually known as Cardano's formula. Poor Tartaglia died penniless and unknown. Clearly, algebra and its development have more than its fair share of drama. I hope you have got to see a little of its magic as we journey through Arabia, India and Greece, solving riddles and problems. For more fun mathematics, don't forget to keep watching The Maths Factor.